Hello, everyone. Welcome to AI at Scale. My name is Yifei, a software engineer in the Facebook ads team. Today, I'm going to talk about large-scale concurrent model development with my colleague, Alex. In today's talk, I'm going to describe a scaling challenge that my team is facing, which could happen to other mature team that is at scale. The growth of the number of ideas. I'll describe the challenge and how we overcome the challenge by introducing a new centralized process. The pros, cons, and new challenges of the new process. Finally, Alex will give some concrete example about practical automation at scale. Let's start with the growth of the number of ideas. In AI at scale, we have discussed how to handle the scale in the data, feature, and model. However, in my team, we see another factor also grow significantly over time. That is the number of ideas. Unlike what you can see from AI conferences, where a company usually publishes only a few big innovations every year, in my team, we receive hundreds of ideas to improve our model every quarter, and the number keeps growing. Those ideas are not always big, innovative, or publish-worthy, but they are essential to improving the model performance. How do we efficiently handle so many ideas? Our solution is to develop a centralized process. I'll first talk about the steps when there is only a single idea, then move to multiple ideas. For multiple ideas, I'll describe what are decentralized and centralized processes. When there is only one idea, the process is simple. Whenever we have the idea, we fork from the baseline, apply the idea to the baseline, test the performance of the new idea. If it is better than the baseline, we launch the new idea. However, when there are two ideas, and if we follow the steps when there is only one idea, we'll encounter some problems. In this graph, both ideas are better than the baseline. However, we start to work on the second idea after the first idea is started, but before the first idea is launched. In other words, there is a baseline change during the development of the second idea. If we directly launch the second idea when it was proved to be better than the baseline, the first idea will be reverted once the second idea is launched. In addition, these two ideas could conflict and interact between each other. If you look at the graph, this is almost the same as you can see from the source control in the traditional software development. When you land a new change, you may encounter a merge conflict. What we normally do in a traditional software development is to resolve the conflict and run the test again. However, the key difference is the model testing cycle is much longer than the traditional software development. In my team, it could take weeks instead of minutes or hours, where we usually see in the traditional software development. To address this issue, we introduced a centralized model development process. When people have an idea, they make a proposal. At a planned cutoff day, we start the centralized process by collecting all the ideas before the cutoff day. From those ideas, we perform a combo design, where each combo is the result of applying one or multiple ideas to the baseline. After the combo design, we test all the combos at the same time and launch the one with the best performance. In this specific example, We have two ideas. We design three combos, that is all the possible combinations of those two ideas. We test all three combos at the same time and launch the best one. In the next section, I'll describe the pros, cons, and the challenges of the centralized process. As for pros, it solves two issues. One is baseline change during the development, where we have discussed in the previous slides. Another pro is, as we have a lot of ideas, most of the ideas are incremental and only bring small gains that is hard to detect during the testing. As we combine multiple ideas into a single combo, it accumulates the gains from multiple ideas, which make it easier to be detected during the testing. There are two cons of this centralized process. First, there is a centralized cutoff time, which means each idea has to wait until the cutoff time to be tested. Second, we need to assign some dedicated engineers to run this process. In terms of the challenges, we have two high-level challenges. First, we like to keep those pros, but overcome the cons. We are working on several projects to increase the throughput of the process, which reduce the waiting time that was created by this centralized process. We are also investing in automation to free the dedicated engineers who run this centralized process. The second high-level challenge is not because of the centralized process itself, but just the challenges to deal with a lot of ideas. For example, how to design combos for hundreds of ideas, and how do we manage those ideas? How do we coordinate different ideas and detect conflicts and interactions between them? And now, I'm going to hand it over to Alex, who will talk about some practical details in the automation area we are invested in.
Thank you, Ife. My name is Alexandra, and I would like to take practical automation at scale. If you look at our concurrent model development process, it has three major steps. First one is preparing the baseline. We usually start with what we already have in production for this model, and then we make some truly required changes. For example, we may update some versions of the dependencies for this model, or we may make the necessary architectural changes that are just needed for it, or remove some features that are no longer available as part of our overall infrastructure. The second step is collecting the proposals. We usually spend quite some time creating the various proposals for various ideas. But at this point, it all comes to the conclusion where we log them into the system, where we add the necessary metadata, where we perhaps annotate them with various properties so that we know better what to expect in this iteration. And then, once we have the baseline, once we have all those proposals, we start working on the combinations of those ideas or proposals, one of which will become the ultimate or next version for the model. So as we talk about the best combo or the best combination, how can we tell which one it is? We have benefits to compare against the costs. We already have some baseline, and we could potentially go with just that. But then looking at the ideas, we see that some of them improve this model in some ways, and some of them bring higher benefits. And furthermore, combinations of those ideas sometimes add up and give us even more benefits or even higher costs, or move the cost in the opposite direction so that models become cheaper and more available to serve. And this exploration is not just ranking them by a single direction. These costs and benefits are slightly more complex than just a single number or a pair of those. Among the benefits, we seek value, higher value to our users. We seek higher value to the advertisers. And also we see higher value to the company itself. Among the costs, we have several. There is a cost to train this model. Perhaps some of those ideas require much more training data, or the training itself, the regime of training becomes more complex relative to the baseline. Then also there is the serve the serve cost for all those models. We need to spend some compute resources, we need to spend some memory, we need to spend some networking bandwidth, and that all adds up, and we cannot have arbitrarily high cost for those things. So how do we get there? What is the process of us understanding those benefits and those costs? The final judge of that is the A/B test. When we run the model that is currently in production side by side with this new candidate and see over time how the two compare. However, this is a very expensive process, as you can imagine, that we cannot do this for arbitrarily many candidates. Also, steps leading to this evaluation, they are also costly. For example, training itself may take quite some time. So we want to build windows to peek into this process and to make decisions the soonest possible. So instead of deferring all the judgment until the very last moment, we try to make some partial judgments as soon as this information becomes available. We train a little, we look a little. We train a bit more, we look at this additional information. And that allows us making those calls, canceling some of the combinations early, and not proceeding to the full end if there is no need for that. So as we do this, we struggle with some challenges of scale. Where does it come from? The number of possible combinations for a given set of ideas is the power set of the number of those ideas. If you only have 3 ideas to explore, you can either take them individually or pairs of those or 3 at a time. But once the number of ideas that you see is 10, 20, 30, then the number of combinations grows exponentially, and you start to need to take some shortcuts and heuristics to identify the promising candidates. The other aspect of scale is just the number of steps. In the previous diagram, I have identified some high-level steps, but there are many more at the lower level, and they introduce additional complexity. Furthermore, this complexity is part of our process. As we explore new ideas, they introduce new complexity into the system. It is not possible to avoid this. We just need a better way to manage it. And finally, the risks that we face through this process, they are compounding. Some early mistake can put in jeopardy the entire process and show if it only shows up at the very late stage. It could force us to reset this entire process and go to the earlier stages and waste a lot of time. So we need some approach, we need some systematic way of addressing the scale, of addressing this complexity and making the overall process manageable. And here we use the Markov algorithm for the individual combinations. Markov algorithm is an equivalent to the Turing machine, only instead of having states and inputs and transitions that are driven by those inputs, Markov algorithm has a list, an ordered list of rules, where each of the rules looks for a specific pattern in the current state, and then if it matches, it executes a particular action affecting that state. And then Markov algorithm goes back to the very first rule and keeps on running down this list over and over again. So in our case, the rules are deliberately simple. For example, one rule is if the model is trained sufficiently well to understand its serving profile, then let's do just that. So we will have a rule that checks whether the model has been sufficiently trained, and if so, it schedules the estimate for its serving cost. Another rule is if the model has been fully trained, we perhaps should send it for the A/B test. And so we have those rules, and the system eventually arrives to the conclusion by following them over and over again over the course of the entire process. As I said, this is equivalent to a Turing machine. So what are the benefits or what are the differences? One difference is that here we anticipate that some of the steps are going to be challenging. We anticipate that some of those innovations, some of those ideas are going to derail the process and make it stuck somewhere in a very inconvenient spot. With the Markov algorithm, we can identify which of the rules are firing, which of the rules are not firing, what are the patterns, what are the violations of the expectations, and go address this by perhaps updating some individual rules in this list and making the system go forward by unblocking it. If it was a state machine and we would try to do this across all those combinations, then we would need to perhaps debug them individually, see what are the similarities, try to better understand the state they are in. But with this Markov algorithm, we are applying enough pressure through the system to converge. And if some of those combinations do not succeed, that is part of the process. We are working in a high-risk environment. Those ideas, they do not always pan out. And having such a flexible system for us to push through this entire process makes the overall system more robust. And this is an approach to the practical automation at scale. Thank you.